Hello, and thank you for joining today's presentation in the Richardson RFPD webinar series, A Walk Around the Block. In today's session, Eric DeRose, Global Product Manager for Supercapacitors at AVX Corporation, discusses the advantages of supercapacitors in power backup applications. So without further delay, let me turn things over to Eric. Eric, go right ahead.
Welcome and thank you for joining the webinar. My name is Eric DeRose and I'm the Global Product Manager for AVX's Supercapacitor product line. Today I'll be briefly covering some basics about what power backup is, some applications, compare batteries and supercapacitors, and then actually show you a mathematical design and example. Let's explore why you should consider supercapacitors for your power backup needs. Secondary power, or power backup, is necessary for when main power runs out or is unexpectedly lost. Think of power backup as an insurance policy. If you never suffer power failure, then no backup power would be required. However, we know energy is not infinite and that circumstances sometimes go beyond our control, so having safety measures built in place for sometimes critical applications makes temporary power backup a necessity. For the wide range of applications that demand power backup, designing in the proper amount of energy can mean the difference of seconds or even milliseconds, and in turn saving or losing data or catastrophic failure. Power backup requirements are often one of the most important design parameters that engineers spend the most time on. For a long time, batteries have been a first thought option for these power backup requirements. As battery size, weight, and environmental and replacement costs have remained a huge burden on these designs in which you may never utilize your power backup insurance policy, longer lasting and more reliable alternative energy storage devices have been gaining more and more consideration. Among them, electric double-layer capacitors, better known as ultracapacitors or supercapacitors, have been likely receiving most consideration instead of batteries. For those unfamiliar, supercapacitors are large energy storage capacitors, typically in the hundreds of millifarads range and up, that bridge the gap between electrolytic capacitors and conventional batteries. As you can see from the application examples depicted on your screen, power backup applications can greatly vary in size from as small as an RTC and handheld devices to as large as railway and utility substations. Batteries have dominated design-ins to these applications, but since costs for replacements and maintenance are very expensive, supercapacitors are growing in popularity. It's fair to expect batteries to continue to dominate, but for suitable application requirements, supercapacitors can provide unique advantages over batteries. Take handheld portable scanners that a worker would use in a shipping and receiving warehouse, for example. Typically, these devices are powered by a lithium-ion battery. Since battery cycle life is short and sees drastic degradation, implementing a supercapacitor not only is valuable for backup in case the battery suddenly dies, saving scanned data, but it also can provide pulse power if this scanner is connected on a network transmitting that data while in use. This would naturally extend lifetime of the battery and in turn reduce battery replacement costs. A larger scale example would be in wind turbines for power and emergency pitch control. In this application, power is needed for about 30 seconds or so when utility power is lost and the blades need turned to stop the rotor. Since the battery bank is located up the tower in the hub and it is a two-person task that requires majority of a day to swap out, replacement and maintenance costs on these wind turbine systems are very high. According to the United States Geological Survey, a U.S. government scientific agency, at the time of January 2019, there were over 58,000 wind turbines in the U.S. wind turbine database, and on average, 3,000 more are installed every year. Just imagine the cost impact of system maintenance and battery replacements every year. In general, though, power backup requirements continue to evolve as system designs grow more intricate and require more functions, and as a result, the number of applications that could potentially use supercapacitors expands. Let's compare batteries and supercapacitors a little side by side. Batteries operate on a chemical reaction which we consider slow energy storage. Since batteries have much higher specific energy than supercapacitors, this means they can provide much longer runtime. This is ideal for steady state power and keeping the system on during normal use. Supercapacitors store energy in an electric field and are referred to as fast energy storage. Supercapacitors have higher specific power, meaning they can deliver larger amounts of current in a defined time interval or instantaneously. The spider web chart to the right is an excellent simplified visual comparison of batteries represented by the red line and supercapacitors represented by the green line, and their fundamental electronic characteristics. Supercapacitor advantages such as long cycle life well into the hundreds of thousands of cycles and beyond, wider operating temperature range, higher load current handling capability, faster charging times, full depth of discharge, and environmental safety and commercial acceptability are all key reasons why supercapacitors are growing in popularity over battery systems in power backup applications. And while batteries hold their own advantages over supercapacitors as well, with continual technology advancements among supercapacitor research and development, such as with higher energy density materials, you can fully expect supercapacitors to keep pushing the limits and steady rise in adoption. Although limited in total storage energy, supercapacitors prove able and advantageous to replace your battery backup system. With the endless expensive system maintenance costs spent on battery replacements and servicemen overhead, if you knew that a supercapacitor backup system could lead you to savings and extend the lifetime of your product, why would you not at least explore the possibility of implementing supercapacitors into your design? Supercapacitors have much longer cycle life. They're typically rated for 500,000 cycles or more when cycled between rated and half-rated voltage under constant current. Taking that further, supercapacitors allow for faster cycling, or charge and discharge, and full depth of discharge to 0 volts. Depending on the battery technology, you may only get hundreds or low thousands of cycles out of it before it needs replacement, and cycling is very slow and you cannot discharge a battery to 0 volts. A supercapacitor's operating temperature range is typically from minus 40 degrees C to plus 85 degrees C, but some electrolyte technologies allow for operation down to minus 55 degrees C and upwards of plus 90 degrees C. Batteries tend to cease up around minus 20 degrees C on their lower end of the range and top out around plus 50 to plus 60 degrees C. As focus on renewable and clean energy continues to grow and concerns about disposing of batteries persist, supercapacitors hold a clear-cut advantage in disposing and handling of these devices. Think about every time you board an airplane now and the gate check crew member asks if you are carrying lithium-ion batteries with you and that they must be removed and left behind if you are. Luckily, these same commercial worries about supercapacitors do not exist. Supercapacitors are also more lightweight, allowing for physical relief to the design and servicemen performing maintenance. So now you're thinking about using a supercapacitor cell or module in your next power backup design? Here are some key design considerations you should be checking and double checking. What is the voltage range in use? If there's a glaring pitfall of supercapacitors, it's that as individual cells, they are lower voltage devices. As such, you'll need to connect multiple cells in series to increase the working voltage. What is the operating temperature range? Sure, you can capture a wider usable operating temperature range with supercapacitors instead of batteries, but understanding how temperature affects lifetime of the capacitor and your product is extremely important. How much energy or power is needed? Supercapacitors are rated in millifarads or farads, but understanding and converting that to joules of energy or watts of power and vice versa is doable when you have the total picture of your application. How long is holdup needed for? It never hurts to over-design as well to have some buffer and account for aging of the device. What are lifetime expectations? This is first a question of your product design, and then in turn a question of expected lifetime of the supercapacitor and understanding how you need to reach that. Are there space constraints to the design? Depending on the amount of power needed, a supercapacitor design may require allowable space and a different configuration in comparison to a battery design. In general, ideal backup systems for supercapacitors would be, but are not limited to, where operating voltage is less than or equal to 12 volts, operating temperature range is between 0 and plus 85 degrees C, and necessary backup time is 120 seconds or less. Let's look at a real design example by the numbers. Let's say the system needs to provide 5 amps from 12 volts down to 9 volts for a goal of at least 5 seconds. To save time, I have already determined we'll need to use 2.7 volt 100 farad cells for this design and 5 of them in series to get to a total rated solution of 13.5 volts and 20 farads. Keep in mind that putting supercapacitors in series will divide the total capacitance depending on number of cells in series, and that oppositely, ESR is multiplied by the same number of cells in series. Reconfiguring the basic I equals C dV dt equation and factoring in voltage drop due to resistance and leakage current of the capacitor, based on these parameters, we can successfully achieve the necessary holdup time. But remember I mentioned it's a good idea to over-design to have some buffer and account for aging of the supercapacitor? Industry aging limits of a supercapacitor, or what's deemed end of life, is when the supercapacitor reaches 200% of its specified ESR value or loses 30% of its specified capacitance value. Therefore, to account for aging and ensure that the supercapacitor can still provide enough holdup time at end of life, we like to encourage using these multipliers when solving. As you can see, this module solution of 5 2.7 volt 100 farad cells in series can successfully provide at least 5 seconds of backup time to the design given all parameters and through end of life of the capacitor. It is my hope that from this webinar I have highlighted how supercapacitors can be better suited for power backup applications based on function and cost savings over batteries. Hopefully next time you'll consider all the design factors to determine if a supercapacitor is appropriate for your application needs. On behalf of AVX and Richardson RFPD, thank you for your time and for tuning in today.